Hello everyone. Here is topic 2 for exam 2. These are the derivatives of the inverse trigonometric functions. So based on what we did before, as you can imagine, the dealing with right triangles and the Cartesian coordinate system, the Pythagorean Theorem is used for right triangles, and essentially that's where all of these fancy denominators are coming from. Basically the Pythagorean Theorem is we're going to show. And so these functions look really complicated, but they're really rather easy. You just have to understand our notation, the derivative with respect to x of this type of thing. So the inverse sine of a function of x. So we just basically have to fill it in. It's du dx, the derivative of our u, over the square root of 1 minus u squared. Then you can see the inverse cosine is just the opposite of that. We have the formula for inverse tangent. Inverse cotangent is just the opposite of that. And our formula for inverse secant. And the inverse cosecant is just the opposite of that. So you want to do your best to memorize these, or at least become familiar with them. I will supply them to you on an exam. But in particular, when we start looking at integration, you want to make sure you're familiar with these types of forms. But let's prove, and we will have a proof quiz on this in the future as well. Let's prove the derivative of the inverse sine of u. And so our theorem is to let u be a differentiable function of x. And if y is the inverse sine of u, then we want to show dy dx is d dx over the square root of 1 minus u squared. So we're going to start by letting y equal the inverse sine of u. But I want you to state immediately that this is where the range of y, so the range of the inverse sine of u, is between negative pi over 2 and pi over 2. So if you recall, we had basically shown that in order to force the sine function to be 1-to-1 so that it has an inverse, we had to restrict its domain to negative pi over 2 to pi over 2, and then once we took the inverse, that became the range. So I'd like you to state that immediately. Okay, now by definition, because we can't work with inverse trig functions directly, by definition we could say that the sine of y is equal to u. And then we could actually start the differentiation process. So I'm going to throw this d dx notation in front of each side. Remember, if you're going to use this, it is optional, but if you are going to use it, make sure it's in front of the term, because it's a differential operator. It's not like we're multiplying by d dx. We're indicating that we're about to differentiate implicitly with respect to x. And the thing is, we already know what the derivative of sine is. And we know the derivative of sine is cosine of the same argument y, but then the derivative of the argument, but the derivative of y implicitly with respect to x is dy dx. And that's equal to, okay, if you took the time to show the d dx notation, all you have to do is be able to read this. It means the derivative of u with respect to x. So therefore, just simply du dx. Okay, so at that point, we've already generated the derivative, dy dx. So let's solve for it. And we do so by just dividing both sides by the cosine of y. So we have that dy dx is du dx over the cosine of y. And at that point, excuse me, what I'm going to do is I'm going to save this. I'm going to box it off, and I'm going to write the word save, because we're going to come back to it. Because if you look at what we're trying to prove, we're trying to prove that the derivative of y with respect to x is equal to du dx over the square root of 1 minus u squared. And so we already have du dx over, but we have instead the cosine of y. So therefore, if we could show that the cosine of y is equal to the positive square root of 1 minus u squared, then we could make a substitution into our result here, and we would be finished. So to begin with, what we're going to do, and what motivates us to do this, is the fact that more than likely this is coming from the Pythagorean Theorem, the square root of 1 minus u squared. So we're going to write the Pythagorean Theorem, or I should say by the Pythagorean identity, because the theorem itself is c squared equals a squared plus b squared. But in terms of an identity, recall, and we're going to do this with respect to sine and cosine, because obviously those are the trig functions. So we could say sine squared, and let's use the angle y, plus cosine squared of the angle y is equal to 1. Now, we know, and you don't have to write this, what I'm going to put in red, but since the sine of y equals u, and this is from the definition, right? Given y is inverse sine of x, we wrote sine of y as u. So since the sine of y is u, we could replace the sine of y by u, and we would have that u squared plus cosine squared y is equal to 1. And then we could solve for cosine of y. But when solving for cosine of y, our first step is to transpose the u squared. So we get that cosine squared of y equals 1 minus u squared. And then we can consider taking the square root of both sides. So cosine of y would be equal to, now I'm going to leave a little space in front of the square root. And so we'll have the square root of 1 minus u squared. But we should know that the reason why I left that little space in front of the square root is because it is a theorem of algebra that if we take the square root of both sides of an equation, we have to introduce a plus or minus to one of the sides. So you have to introduce the plus or minus there. So we don't automatically come up with the positive square root of 1 minus u squared. We came up with plus or minus the square root of 1 minus u squared. So now we have to argue why it is that we're going to be able to take only the positive square root of this. And so you want to write a nice college-like sentence here, and this is going to be 3 things we'll address. We'll say that the range of the inverse of, let's even go so far as to state it this way, the range of y, which equals the inverse sine of u, is from negative pi over 2 to pi over 2. Okay, so we basically restated what we wrote up here, right? When we let y equal the inverse sine of u, we had stated the range, so we repeated that. So the range of the inverse of y equaling the inverse sine of u is negative pi over 2 to pi over 2. Okay, this means that the angle y is in quadrants 1 or quadrant 4. So remember, this range is an interval, and it accounts for the two quadrants 1 and 4. So the only place y can be in is in those two quadrants. Well, if you think of our little gimmick, you don't have to write this down, but remember that all students take calculus tells us where the trig functions are positive. If you think about the cosine function in particular, it's positive in 1 and 4. So cosine does not have a choice. See, the angle y is forced to be in quadrants 1 and 4 by the definition of the inverse sine, and then as a consequence, the cosine happens to be positive in both of those quadrants. So we can continue and say, therefore, cosine of y must be positive, and then we can finish it up. And let's use some fancy math jargon here. We'll say, hence the cosine of y. We've now proven that we could take it only to be the positive square root of 1 minus u squared, and then I'll finish it up with a thus, and we'll go back and we'll restate that we had already shown that dy dx was du dx over the cosine of y, and now we could replace the cosine of y by the positive square root of 1 minus u squared, and we have our du dx in the numerator, and that ends the proof. Okay, so you're going to have a proof quiz on this, and it's only the one proof, so it is a proof that I would say memory, they're bound to make a mistake. So hopefully, in terms of my commentary, you'll practice it a couple times and form an understanding of it. Okay, but now just the mechanics of some derivative problems. So we got a couple pages, bunch of different examples, trying to show you all the different types of situations. We have the definitions on the first page, but also I have this document posted in Blackboard, and this will be your cheat sheet for the second exam. So you can see we have the derivatives of all 6 inverse trig functions, and then corresponding integration formulas that we'll talk about. But use this, and for our first example, we've got the inverse secant of 3x. And so you basically just follow the formula for the inverse secant of u in this example. So with regards to the formula, okay, this would be dy dx, y prime, whatever you prefer. Okay, it's a fraction. I always fill in the denominator first, it's your choice, but in the denominator of the fraction is the absolute value of u, and in this case u is 3x, and then underneath the radical, the square root of u squared minus 1. Now u is 3x, so when we make that substitution, make sure you put parentheses around it and indicate that it's being squared, and then as part of the formula minus 1, and then simply du dx goes in the numerator, and du dx is the derivative of u, which is 3x, and so that's just simply 3. So with regards to the formula, Once again, it's du dx, absolute value of u, square root u squared minus 1. Let me just clean that up a little. Okay, so we're just following the formula. Now, one thing we could do, a couple things though to finish this up. You can cancel, we're definitely going to have to square this 3x as I mentioned. You can actually cancel these 3's. You can cancel inside the absolute value with a numerical, with a number, okay, but not with a variable, okay. So I can cancel those 3's, and then I'd have that dy dx is, right, in the numerator looks like we just have 1, in the denominator absolute value of x, and then the square root of, as I said, make sure you square the 3x, that's 9x squared minus 1. Okay, number 2 is an example where we have a sum of 2 terms, and we know we can differentiate term by term, and we also know that these constant multiples of 5 and 3 tag along in the differentiation process. And so we look for the formulas for the inverse sine of u, inverse cotangent of u, and we have formulas for those. So uppercase f prime of x is going to be, okay, term by term, the 5 is going to tag along as a constant multiple, differentiating the inverse sine. Okay, reference the formula sheet, and for the inverse sine, we have in the denominator the square root of 1 minus u squared. So that's the square root of 1 minus, u in this case is 2x, but that as a quantity has to be squared. And then the numerator du dx, you could just matching up the formula. And du dx is just the derivative of u in this case, which is 2x, so that's 2. Go to the next term, plus 3 tags along as a constant multiple, differentiating the inverse cotangent of u. Follow the formula. So here it is. Go to the inverse cotangent of u. Okay, fraction like all of them are. And in the denominator, no radical for this one. It's just 1 plus u squared, but u in this case is 4x. And that'll have to be squared. And then in the numerator, the derivative of the argument 4x, which is 4. Okay, so make sure you're following the formulas. And simplifying. In the denominator of the first term, we have 1 minus square the 2x to get 4x squared. And multiply the 5 and the 2 in the numerator to get 10. And then plus, actually, I'm sorry, I made a mistake there. It should be a minus, because the formula for inverse cotangent, recall, was a negative. And so we'll make this minus. And then we'll put a 12 in the numerator and 1 plus. Make sure you square that 4x to get 16x squared. Okay, so those were just single applications of the formula, essentially. And then we can have anything involved. Products, quotients, powers, exponentials, logs, standard trig functions, pretty much anything can be thrown in the mix. So for number 3, hopefully you identify this as, well, let's look at it together. Inverse tangent of 4x, that's a function of x on its own. E to the 5x is a function of x, call them u and v respectively, and we're going to need the product rule. So once you identify that you need the product rule, q prime of x would be the first factor, e to the 5x, derivative of the second. Now we need our formula for inverse tangent of u. So again, reference the formula sheet. Here's the inverse tangent right here. Fraction, 1 plus u squared in the denominator. U in this case is the 4x, but again that has to be squared. And in the numerator, du dx, u is the argument of the inverse tangent, 4x again, its derivative 4. So there, with regards to the product rule, is the first factor, derivative of the second. Now plus the second factor, inverse tangent of 4x, and then times the derivative of the first. I'm going to throw some parentheses around that. Derivative of the first, now I'm differentiating e to the 5x. The derivative of e to the u is e to the u, so recopy e to the 5x, but then don't forget times the derivative of the power on the base of e. So the derivative of 5x, which is 5. And with respect to the product rule, there's uv prime plus v and u prime. And then to rewrite this, t prime of x is equal to, let's see, as a fraction, in the denominator, 1 plus, make sure you square this 4x, so we get 16x squared. And then in the numerator, we'll put the 4 out in front of the e to the 5x. And then for the second term, let's bring the 5 and the e to the 5x out in front of the inverse tangent of 4x. Okay, so in number 4, breaking it down, I try to identify the primary rule of differentiation. We have inverse cotangent of this quantity, so that's a function of t on its own, being multiplied obviously by t to the 5th. So treat them as u and v respectively, and it looks like we're going to need the product rule again. So by the product rule, if you're going to use differential notation, it would be dy dt. And that would be equal to the first factor, t to the 5th, times the derivative of the second. Okay, now we need our formula for inverse cotangent of u. So look at the formula sheet if you need to. And for the inverse cotangent of u, we have a negative in the denominator, 1 plus u squared, and du dx in the numerator. So let me put the negative up here right away so I don't forget. And then in the denominator, 1 plus u squared, but u is e to the 5t. So 1 plus e to the 5t is a quantity squared. And in the numerator, the derivative of that u. And so now we're differentiating e to the 5t. That's our formula for e to the u, which we repeat, e to the 5t, but then don't forget times the derivative of the power. And differentiating 5t, we get 5. Alright, that's just the first part of the product rule. That is, here's our u, and then all of this represents v prime. But now we need to finish it up, of course. Plus v, second factor, inverse cotangent of e to the 5t, and then times the derivative of the first, and the derivative of t to the 5th, just simply 5t to the 4th. And that finishes up the product rule with our v and our u prime. Okay, and then we'll clean this up, make it look a little more respectable. dy dt would then be equal to, okay, as a single fraction in the denominator, we'll have 1 plus, okay, square this e to the 5t, just behaves like any other common base, or any other base that is. You take a power, you raise it to a power, and you're going to multiply the exponents, so that should be e to the 10t. And in the numerator, let's see, we have the minus 5, the e to the 5t and the t to the 5th. So the appropriate order, minus 5, t to the 5th, e to the 5t. And then this would be plus, let's bring the 5t to the 4th out in front of the inverse cotangent of e to the 5t. Okay, so I think I'm going to stop right there, and we'll come back and do a part 2 for this topic. So we'll see you when you are ready.